Alright, so let's do the third part of the lecture 2. This will be all about inhibitors. So we're gonna start out with the competitive inhibitors. What the competitive inhibitor does is that there is the active site, right? And then instead of the substrate binding, the inhibitor can actually bind to that site, so that the substrate cannot actually bind to the enzyme. Thus the reaction doesn't happen. So that's pretty much what the competitive inhibitor does. So let's just create the scheme for the this reaction right here. So this portion right here doesn't really change that much, except that I do actually add the I to everything here. But when you actually have the free E, that free E can actually become EI complex. And when they do, S become unreactive. So I actually put this reaction right here to be the reaction 1, and then ES becoming the product becomes the reaction 2, and then the inhibitors binding to the enzyme becomes a reaction 3. So I think I'm gonna probably go slower for the first one. So for this one, I am going to apply the fast steady state approximations for the ES complex right here. So the concentration of ES is not going to change, means that this becomes 0. So ES can be formed from here, right? That will be the forward reaction of that. That's this one right here. And then ES can disappear by forming the product. That's going to be the negative. And then going backward to the EMS, right? So overall I have these things is equal to 0. So if I solve for E right here, you get these things right here, which the very first portion right here, the 3 rate constant become Km. So Km ES over S is equal to E. Let's think about this portion right here. So the formation of EI is constant, so that the concentration of the EI doesn't change, right? So the EI can actually formed by going backward, the K minus 3. So that's going to be positive. And then dissociation can go back to the original reactant, right? That's going to be the negative value right here. And once again, if I solve for the EI for this one, I get these things right here. So this become that. And then if I actually put Ki to be this value right here, then Ki is going to replace this one, then I get this one right here. And then that E, I'm substituting this E right here, right, by that one. Also that's going to go in here. So replacing this and that by the Ki, and then replacing this EI from here, you get these things right here. So once we get these two relationship, I can actually do the mass balance here. The mass balance, the original concentration of the E naught should be equal to the E plus ES plus EI, right? The all species added should be same as what you started out with, right? So E can be given by that guy, but that contains ES, and then ES contains ES, and then EI contains ES. So factoring out ES, you get this formula right here. So that's promising because I can actually now isolate ES. ES is equal to this one divided by that portion right here, right? So I get this one. And note that I have everything that's written in here is in terms of the stuff that we assume that we know. The original concentration of the enzyme, original concentration of the inhibitors, and then the concentration of the substrate. If I all know those guys, then ES can be described purely by the stuff that you already know. Now, once I get the ES, that one, the right before the product formations, then I can describe the rate constant, the rate expressions, to be that rate constant multiplied by ES, and that ES is replaced by that guy, you get this one. Now, by setting Bmax is equal to K3E0, and that makes sense, right? Because if all the starting out enzyme is actually having react with the substrate, right? That's when the maximum rate happens, right? So the Bmax is equal to K3E0, and that will replace that one and that one, and then I get these things right here. Now I can actually simplify a little bit more about this portion right here. So that expression can be actually given by that form right here. Only thing I did is just a slight algebra manipulations from here to here. Basically, I just divide top and bottom by S. That's pretty much all I did. Now, I'm gonna actually make the line Weaver plot of this guy. Simply, I'm going to mimic the simple Michaelis-Menten stuff. So, when I was actually working with the Michaelis-Menten, I did the 1 over B, right? 1 over 8 is equal to the AX plus B, right? So, I'm gonna do the same stuff. 1 over B, it's gonna flip, and then that's gonna separate into two terms, right? This term and that term. And then I can also isolate this 1 over S being the X variable here. So Y is equal to A X plus B right here. So immediately, if I actually compare this line Weaver plot for the simple one and the competitive inhibitors, I can immediately tell that the y-intercept is not going to be changed. And let's look at this slope right here. Concentration is always positive, and then the equilibrium constant is always positive, right? So this number right here is bigger than 1. So compared to this slope right here, that slope right here, this is bigger, right? Because it's bigger than 1 here. So it has it crosses the y line, y-axis, exactly the same spot, but it will be more slope. And let's just try to see what the Km is going to be. So the Km, by definitions, if I follow what I was actually talking about previously, the Km, 1 over Km is equal to 1 over S at the y value is equal to 0, right? So I'm going to put this value to go to 0, right? Then what can I do here? So the Km over Bmax 1 plus I over Ki, right? 1 over S naught is equal to minus 1 over Bn, right? Because that's, I can actually put these things on the left hand side, right? Then Bm is going to cancel, right? So Km, why don't I just divide this Km on both sides? Then this is what I get. The concentration, when the X actually crosses the line actually crosses the X-axis, it's going to be a smaller value. So I'm talking about this one right here. As I said, that the Y intercept is exactly the same as the normal case or the inhibitor case, but the X-intercept is going to be much smaller, and that's because of that one right here. Now, because if you divide both sides by that, then that becomes this plus that, right? And that value right here is bigger than 1. So I think that's probably good enough for this one. The non-competitive inhibitors is slightly more complicated, because non-competitive inhibitors actually attach to the enzyme in a different place. So it really doesn't block or anything like that. It just attaches to somewhere else so that it changes the form of the enzyme. And by changing the form of the enzyme, it doesn't really react with the substrate anymore. Now, this one, it depends on who you talk to, I think, but probably the natural thing is that you can actually make them completely independent of whether the S is attached or not attached. This inhibitor can actually attach to the enzyme. So enzyme inhibitors can attach to the free form of E and ES at the same time. That makes this reaction scheme a little bit more difficult. So originally we start out with this simple reaction, right? Now we're going to add these two conditions. E and I can form EI, and then ES and I can form ESI. And all of these things are done by the equilibrium constant. That makes our life a little bit simpler. So this one right here, the equilibrium constant, product over reactant, you get EI divided by EI, right? And then the same stuff here, ESI over ESI, right? And then Km, pretty much the same stuff from the previous one. It comes from the steady state approximations. What's being formed is the KRES plus KBES should be equal to what becomes the ES, right? That's KF times E times S, right? So you can actually rearrange that one to get this one. That's Km right here. And then doing the mass conservations, I get E naught is equal to all the chemical that contains E, right? So E and EI and ES and ESI. Okay, now it's kind of interesting in a way that I can actually calculate EI from that expression, or the ESI from that expression right here. So defining that alpha being that term and then alpha dash being that term right here, then E naught becomes alpha times E. So let's just think about this one. Alpha times E. Alpha is 1, right? 1 plus this things, right? So 1 times E, that corresponds to that value right here. And then I divided by K1 multiplied by E. That comes from this one right here, right? So if I actually solve for EI right here, that's E I divided by K1, right? That's K. So that's this one, right? Multiply by E, you get EI. So that portion right here represents that one. And then similarly, these things are represented by that one right here. 1 times ES is that one. I times K, that's capital K, K1 dash. You get it from here, you get this one right here, right? And then from that, the Km is equal to ES divided by ES. So I can do a little bit more about this E here, right? E can be represented by Km, oh, that K is horrendous. Km ES Km ES over S, right? I don't know why my pen is not working, but it's S, right? That's also S right here. So by doing that substitutions, you get this term becomes that one, right? Now I can actually factor out ES here. You see the pattern that you start out with a steady state for the equilibrium constant, and then that substitute and then plug it into the mass balance, and then factor out the ES, and then you solve for the ES, right? So factor out ES and then solve for ES and then plug it into this guy, you get the rate expression to be that one right here. So if I actually write out the rate expressions, I can write it in that form right here. And once again, if I want to convert this one into the Lineweaver back plot, I'm gonna do 1 over b, right? And 1 over b is equal to, I swap this and then I separate because there's a positive sign, right? So I swap and then separate into 2 terms. One term contains 1 over s, that's that one, and then the term that doesn't contain s term, it's gonna be y-intercept. So ax plus b, right? Basically. Right, that's pretty much what I have here. So let's actually think about some case here. What would be the y-intercept here. The y-intercept is going to be Bmax divided by something. The division of the division, you can actually put it in the top, right? And then that's bigger than 1. So what it means is that when you actually put this one to be 0, x to be 0, right? Then that value right here should be higher than this guy, right? So let me just check. The non-competitive inhibitors, right? The y-axis, the y-intercept is going to be higher than the original one, right? Original one is right here, right? Higher. Now what about the Km? Now I'm going to have to solve this one. Again, this things to be equal to 0. Wow, my pen really isn't working very well. Alright, so when I actually solve this one, remember that this is a non-competitive inhibitions, right? Meaning that it's nearly independent of whether the substrate is attached or not attached. Meaning that these things right here is nearly identical. So remember that one is supposed to be on top, right? So these guys are cancelled. Then what's going to happen is that Bmax is going to cancel. I get the Km over S is equal to 1. That means that when the line goes across the x-axis, Km value is pretty much unchanged compared to the non-inhibitors, just because it's the same stuff here. What you get for that one and what you get for that one is pretty much the same here, right? So you get exactly the same x-intercept here. So we are done with that one and we are done with that one, right? So let's talk about the uncompetitive inhibitors. The uncompetitive inhibitors only binds to the enzyme when substrate is bound to the enzyme. Now that's the third version, right? So this one is slightly simple scheme-wise, meaning that you have pretty much the same equations from the last one, except that I have only one additional reactions where that this ES and I can actually form ESI. This one is not going to form EI. So I have that one, the K3 equilibrium constant, product over reactant, and then Km being exactly the same by the steady state. And then I go to the mass conservations, and then I'm going to substitute some of these guys. So Km ES over S is equal to E, and then ESI is equal to ESI over K3. I can actually substitute this E with that one, and then I can substitute ESI with that one right here. Look, I already have the ES on everything, so I can actually factor out the ES, right? And then solve for the ES, right? Then when you solve for the ES, all you gotta do is that you're gonna have to plug these things into the product formation rate expressions, which is this one right here. So that is gonna go into here. And then K3 times E naught, once again that the K3 times E naught is that if all enzymes are attached by the substrate, right? Then that becomes the Vmax, right? So that's a Vmax right here. And then if I multiply top and bottom by S, I get this things right here. So once we get the rate expressions, I'm gonna actually do the same stuff again. The Lineweaver backplot 1 over B is equal to this things right here. Flip and then separate, right? I get this things right here. So for this one, it looks like that I do actually have some higher y-intercept, right? Because division of the division goes to the top, and then this number right here is bigger than 1, right? Guaranteed, because they're positive numbers, right? So y-intercept is going to be higher, but slope right here is going to be exactly the same. So what does it look like? We get like this. It's parallel line. So I think I pretty much covered everything about the inhibitor stuff. There is some other things called the suicide inhibitors maybe, but I'm just too lazy to cover that one, so this is good enough.